Dear students, you already know about the laws of chemical combination and stoichiometry of reactions and chemical processes. Now, let us study a little more about the structure of atoms. The scientific world and the philosophers were all involved in the quest about what is there in the matter beyond what we can see through our eyes. What is the matter actually made up of? As early as 400 BC, Indian and Greek philosophers had proposed the existence of atoms. They were of the view that atoms are the fundamental building blocks of matter. According to them, the continued subdivision of matter would ultimately yield atoms which would not further be divisible. The Indian philosophers like Kannad had given the subdivisibility of matter. The word atom has been derived from the Greek word atomio, which means uncuttable or non-divisible. These earlier ideas were mere speculations, and there was no way to test them experimentally. These ideas remained dormant for a very long time and were revived again by the scientists in the 19th century. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton in 1808. His theory, called Dalton's atomic theory, regarded the atom as the ultimate particle of matter. He based his theory on the findings of the laws of chemical combination that you have already studied. Can you tell me which laws are in accordance with his theory? Yes, Dalton's atomic theory was able to explain the laws of conservation of mass, law of constant composition and law of multiple proportion very successfully. However, it failed to explain the results of many experiments and observations about the properties of matter. For example, have you ever tried that when you rub a comb on your hair and then try to lift paper, it gets lifted? Similarly, they were not able to explain why substances like glass or ebonite, when rubbed with silk or fur, get electrically charged. Why substances like glass or ebonite, when rubbed with silk or fur, get electrically charged. In this unit, we start with the experimental observations made by the scientists towards the end of the 19th and beginning of the 20th century. These established that atoms are made of subatomic particles, that is, electrons, protons and neutrons, a concept very different from Dalton. So, let us see how the discovery of subatomic particles began. An insight into the structure of atom was obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep in mind a basic rule regarding the behavior of charged particles, that is, like charges repel each other and unlike charges attract each other. So, let us see how the discovery of electron came into being. Now, during this time when the scientists were trying to find out what is the smallest particle of matter, they were trying various ways of breaking the matter further and further, maybe by using some mechanical pressure like hammer, heat or even passing an electric current through various materials. In 1830, Michael Faraday showed that if electricity is passed through a solution of an electrolyte, chemical reactions occur at the electrodes, which resulted in the liberation and deposition of matter at the electrodes. He formulated certain laws which you will study later. These results suggested the particulate nature of electricity. In mid-1850s, many scientists, mainly Faraday, began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes, as depicted on the screen. A cathode ray tube is made of glass containing two thin pieces of metal called the electrodes. These electrodes are sealed inside the glass tube. The electrical discharge through the gases could be observed only at a very low pressure and at a very high voltage. The pressure of different gases could be adjusted by evacuation of the glass tubes. When the sufficiently high voltage is applied across the electrodes, current starts flowing through a stream of particles moving in the tube from the negative electrode, that is cathode, to the positive electrode, that is anode. These were called as cathode rays or cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating the tube behind anode with phosphorescent material like zinc sulphide. When these rays, after passing through anode, strike the zinc sulphide coating, a bright spot is developed on the coating. The results of these experiments were: the cathode ray starts from cathode and moves towards the anode. These rays themselves are not visible, but their behavior can be observed with the help of certain materials like fluorescent or phosphorescent, which glow when hit by them. A television picture tube is a cathode ray tube, and television pictures result due to fluorescence on the television screen, which is coated with certain fluorescent or phosphorescent materials. The third observation was that in the absence of electrical or magnetic field, these rays travel in a straight line. In the presence of electrical or magnetic field, the behavior of cathode rays are similar to that expected from a negatively charged particle, suggesting that the cathode ray consists of negatively charged particles, and these particles were named as electrons. The characteristics of cathode rays, that is electrons, do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tube. Thus, we can conclude that electrons are the basic constituent of all the atoms. You understand that? Because whatever be the nature of the gas, the cathode ray particles are exactly the same. That means electrons are the basic particles of all matter around us. Now we need to find what is the charge to mass ratio of the electrons. In 1897, British physicist J.J. Thomson measured the ratio of electric charge E to the mass of electron m.e. by using cathode ray tube and applying electrical and magnetic field perpendicular to each other as well as to the path of the electrons. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Similarly, when only magnetic field is applied, the electrons strike the cathode ray tube at point C. By carefully balancing the electrical and magnetic field, it is possible to bring back the electron to the path which is followed in the absence of electrical or magnetic field, and they hit the screen at the point B, that is straight. Thomson argued that the amount of deviation of the particles from their path in the presence of electrical or magnetic field depends upon the magnitude of the negative charge on the particle. Greater the magnitude of the charge on the particle, greater is the interaction with the electric or magnetic field, and thus greater is the deflection. The mass of the particle is also one of the component on which this depends. That is, lighter the particle, greater the deflection. Next component is the strength of electric or magnetic field. The deflection of the electron from its original path increases with the increase in the voltage across the electrodes or the strength of the magnetic field. By carrying out accurate measurements on the amount of deflections observed by the electrons on the electric field strength or the magnetic field strength, Thomson was able to determine the value of charge to mass, that is E by me, as charge upon mass is equal to 1.758820 multiplied by 10 raised to the power 11 coulombs per kg. My dear students, you must be thinking it is a difficult task, but if you have the urge to find answers to the questions, you will always do that, and that is how scientists work. They find the questions and then try to find answers, and that's how you should also go about. Maybe not such difficult ones, but yes, whatever you see around yourself. Ask questions why this natural phenomena is occurring and try and find answers. Now going back to Thomson's charge to mass ratio, where me is the mass of the electron in kg and E is the magnitude of the charge on the electron in coulombs. Since electrons are negatively charged, the charge on electron is minus E. Now the task was, what is the charge on the electron? See, J.J. Thomson gave the charge to mass ratio. This task was taken up by R.A. Millikan from 1868 to 1953, known as oil drop experiment from 1906 to 1914. Long time for research, yes. And to determine the charge on the electrons, he found the charge on electron to be minus 1.6 into 10 raised to the power minus 19 coulombs. The present accepted value of electrical charge is minus 1.602176 multiplied by 10 raised to the power minus 19 coulombs. The mass of the electron, represented as me, was determined by combining these results with Thomson's value of charge to mass ratio. So, the task of finding the mass is equal to charge, that was found by the Millikan from Millikan oil drop method, and divided by charge to mass ratio, which was given by J.J. Thomson. So, let us do that. 1.602 into 10 raised to the power minus 19 coulombs divided by 1.758820 multiplied by 10 raised to the power 11 coulombs per kg. So, the mass of electron on calculations comes out to be 9.1094 into 10 raised to the power minus 31 kilograms. So, my dear students, you now know how the mass of a tiny particle which we can't even see was found by finding charge by J.J. Thomson and charge to mass ratio found by Millikan oil drop method. We have also learned about one type of particles that make up the atom. These are the negatively charged electrons. Now, the task in front of the scientists was, as the atom is neutral, but the electrons are negatively charged, the atom should also contain some positively charged particles to neutralize the charge on the electrons. So, some more experimentations and brainstorming to come to a conclusion were done. And for this, electrical discharge on gases was carried out in a modified cathode ray tube, and this led to the discovery of canal rays, which were carrying positively charged particles. After experimentations, it was concluded that unlike cathode rays, the mass of the positively charged particles depend upon the nature of the gas present in the cathode ray tube, because these are simply the positively charged gaseous ions. For example, if we take hydrogen gas in the discharge tube, after the loss of electrons, what we will have? We will have H plus ions. On the other hand, if helium gas is taken, it will have helium plus or helium 2 plus ions. So, the particle would be different. The second observation was the charge to mass ratio of the particles depends on the gas from which these originate. It has to be, isn't it? The charge will depend on the number of electrons that are lost from the atom. Some of the positively charged particles carry a multiple of the fundamental unit of electrical charge. And if I may ask, what is the fundamental unit? We have already studied that earlier. It is 1.6 into 10 raised to the power minus 19 coulombs. So, it was found that some of these positively charged particles had a charge which was multiple of this unit. The behavior of these particles in the magnetic or electrical field is opposite to that observed for electron or cathode rays. The smallest and the lightest positive ion was obtained from the lightest element, that is hydrogen, and it was called a proton. This positively charged particle was characterized in 1919, and later a need was felt for the presence of some electrically neutral particles. Why? Can you think of that? See, for the atom to be neutral, for the electrons, we had protons which could cover the charge, which could neutralize the charge. But now the other thing in the mind of scientists was how to take care of the mass. So, the mass of electrons and protons together was not making up for the mass of the atom. So, new particles were discovered by Chadwick in 1932. He bombarded a thin sheet of beryllium, the element, by alpha particles. When electrically neutral particles having a mass slightly greater than that of the protons were emitted. He named these particles as neutrons. The important properties of all these fundamental particles are presented in the table. So, my dear students, let us have a look at the properties of these elements in the table on the screen. The name of the particles, their symbol, absolute charge in coulombs, relative charge, mass per kg, mass in atomic mass units and approximate mass in units is given in the table. Electron, the symbol is E, and the absolute charge is minus 1.6 into 10 raised to the power minus 19 coulombs. On the other hand, the proton, which has exactly opposite charge to the electron, has plus 1.6 into 10 raised to the power minus 19 coulomb as the charge. So, the relative charges for electron we take as minus 1 and for proton we take as plus 1, and neutron, it is neutral. Mass in kg is given in the table, and then the mass in the units and approximate mass. This is what we need. The approximate mass which we use for our basic calculations and understanding is that for electron the mass is taken as 0 units, for proton it is taken as 1 unit, and for neutron also it is taken as 1 unit. So, my dear students, let us learn more about the story of structure of atom. By now, the scientists have learned that matter is made up of atoms, and atoms are made up of negatively charged electrons, positively charged protons and neutral neutrons. Thus, the structure suggested by Dalton's indivisible atom is now composed of subatomic particles carrying the charges. Now, the major problem before the scientists after the discovery of subatomic particles was how these subatomic particles are arranged in an atom. So, they needed to account for the stability of the atom. They needed to compare the behavior of elements in terms of both physical and chemical properties, to explain the formation of different kinds of molecules by the combination of different atoms, and to understand the origin and the nature of the characteristics of electromagnetic radiations absorbed or emitted by atoms. Dear students, these are the various experiments which were being carried out during the same time. So, whatever the structure of atom was to be proposed had to explain all these observations, isn't it? So, it is all complete alignment of whatever the scientific discoveries were happening during that time. So, different atomic models were proposed to explain the distribution of these charged particles in atom. Although some of these models were not able to explain the stability of atoms, let us discuss two of these models. One proposed by J.J. Thomson and the other proposed by Ernest Rutherford, which intrigued other scientists to think and propose corrections. So, my dear students, this is the nature of science. Science is falsifiable. It is not like a sermon from some learned person. You can question and seek answers. Science is dynamic. Maybe the discoveries that we are learning today, you may come out with some new discoveries and suggest some new conclusions to the structure of atom. Science is also verifiable. It originates from deductive and inductive reasonings. It is a journey from known towards the unknown. My dear students, so if you are feeling that why are we studying something that has been falsified, it is to tell you that science evolves from experimentation, and also we must appreciate the work, because when we fail, from our failures also we learn. So, J.J. Thomson in 1898 proposed that an atom has a spherical shape, okay, with a radius of approximately 10 raised to the power minus 10 meters, in which the positively charged particles are uniformly distributed. The electrons are embedded into it in such a manner as to give it the most stable electrostatic arrangement. So, many different names were given to this model. For example, someone called them plum pudding model. You understand? A pudding. So, in the pudding, if there are some plums which are like that of electrons, so they said it is like a plum pudding. So, the whole pudding is made up of positive charge, and in that pudding the negatively charged electrons are embedded. And some of them said no, it is like a watermelon. So, like the watermelon, the complete watermelon, the red part is like the positive charge, and the seeds, the black colored seeds of watermelon are those of the electrons. So, this model can be visualized as a pudding or watermelon of positive charge and electrons. An important feature of this model is that the mass of the atom is assumed to be uniformly distributed over the atom. This model is able to explain the overall electroneutrality of the atom very well, and for this Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by the gases. But as he published his model in the science journals, Rutherford, who was carrying out his experiments on the matter to establish the structure of atom, came out with his own observations. He said that J.J. Thomson, your model can't explain my experimental observations. So, what were the observations of Rutherford? Let us see. So, Rutherford and his students bombarded very thin gold foil with alpha particles. Can you see what's happening here? First, you have the matter. So, they are hammering it to break into small pieces. Then they are passing some alpha particles and they are bombarding. So, they are trying to see what is there inside, trying to understand what cannot be seen by the naked eyes. So, what Rutherford did? He took a very thin gold foil and bombarded it with alpha particles. Alpha particles, they are the stream of high energy particles from a radioactive source, which were directed at the thin gold foil of approximate thickness of 100 nanometers. You have already understood about various units in the previous chapters. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever the alpha particles struck the screen, a tiny flash of light was produced at that point. The result of scattering experiment were unexpected. According to Thomson model of atom, the mass of each gold atom in the foil should have been spread evenly over the entire atom. But the alpha particles had enough energy to pass directly through such uniform distribution of mass. It was expected, according to the Thomson model, that the particles would slow down and change directions only by a small angle as they pass through the foil. But the observations of Rutherford were entirely different. He observed that most of the alpha particles passed straight through the gold foil undeflected. A small fraction of the alpha particles was deflected by small angles. A very few alpha particles, approximately 1 in 20,000, bounced back. That is, they were deflected by 180-degree angle. You can imagine that if I hit the wall with a ball, what will happen? The ball will bounce back. So, that was the kind of observation that Rutherford made, and he was really boggled that what is it that these fast moving alpha particles are hitting, that they are returning back at 180 degree. So, on the basis of these observations, Rutherford drew the following conclusions regarding the structure of atom. First, because most of the alpha particles were going straight, that means most of the space in the atom is empty. Second, a few positively charged particles were deflected, so he concluded that deflection must be due to some enormous repulsive force showing that the positive charge of the atom is not spread throughout the atom as Thomson had suggested. Just imagine, alpha particles are moving fast and they are positively charged. So, if they are bouncing back or if they are deflecting, that means they are interacting with some positively charged particle inside the atom. So, this made Rutherford conclude that the positive charge has to be concentrated in a very small volume that repelled and deflected the positively charged alpha particles. The third observation was calculations by Rutherford, which showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 raised to the power minus 10 meters, while that of the nucleus is 10 raised to the power minus 15 meters. One can appreciate this difference in the size by realizing that if a cricket ball is represented as the nucleus, then the radius of the atom would be about 5 kilometer. That means the cricket ground. On the basis of these observations and conclusions, Rutherford proposed the nuclear model of atom. According to this model, the positive charge and most of the mass of the atom was densely concentrated in extremely small region. This very small portion of the atom was called nucleus by Rutherford. So, what is there in the nucleus? It is the positive charge and all the mass. The nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular path called orbits. Thus, Rutherford's model of atom resembles the solar system, like sun having the nucleus, and around the nucleus you have electrons, that is like the planets. Now these electrons, which are like the planets, and the nucleus, which is like the sun, are held together by electrostatic forces of attraction. What happens in the solar system? We say that the sun and the planets are held together by gravitational force. Okay? So, here it is the electrostatic forces of attraction. And I am sure after studying all the experimentations that various scientists did, you will be able to draw diagrams to represent their experimental setup, and don't forget to label them properly, because labeling a diagram is also an art. So, to be a true science student, keep observing, collecting data and drawing inferences. That is the essence of science. Happy learning.